All right, in this video, we're going to start our review for the final exam for the 2021-22 school year. Traditionally, the final exam is paper 1. And so we see question number 1. This comes from the February-March administration in 2019. A wave has a frequency of 5 gigahertz. Like right away, we can already sort of do something with that. Frequency equals 5. You should know that giga is a billion. And if we know the frequency, we can calculate the time period right away. So just 1 over the frequency. So 1 divided by 5 billion is 1/5 billionths of a second. Maybe there's a nicer way to report that number. So I'll type it in like this. 5 billion. And this 1 over x key will take the inverse of it. So 1 over 5 billion is that. 2 times 10 to the negative 10. So now the question becomes, which of these is 2 times 10 to the negative 10 seconds? So I'm going to convert each one. I'm going to convert picoseconds to seconds. I'm going to convert nanoseconds to seconds. And I'm going to convert, do the same thing here. And I'm going to convert microseconds to seconds. So there is 10 to the 12 picoseconds in a second. There are 10 to the 9 nanoseconds in 1 second. So that's 10 to the 9th power. Let me make that clear. Same thing here, 10 to the 9 nanoseconds per second. So we're dividing by, a billion for part B and C. We're dividing by a trillion for part A, and we're dividing 20,000 microseconds by 1,000,000 microseconds per second. And we find right away that 200 picoseconds, once you divide it by 10 to the 12, is 2 times 10 to the negative 10 seconds. So there's our answer. Let's sort of disprove the remaining options. So 2 nanoseconds is how long in seconds? Two times 10 to the negative 9, right? So 2 nanoseconds, we can just sort of think about it like that. 10 to the 9 in the denominator is the same thing as 10 to the negative 9 in the numerator. So 2 times 10 to the negative 9 seconds is not 2 times 10 to the negative 10. 20 nanoseconds is just sort of 10 times more than this, right? And so this would be 2 times 10 to the negative 8. So this would sort of goes the opposite way. We need 0.2 nanoseconds, right? Would be the same as this, but that's not one of our choices. So it's not 2, it's not 20, right? Which is sort of going the other way. 20,000 microseconds. So that's a lot of microseconds, but a microsecond is 1,000 times smaller than a nanosecond, right? We're sort of in picoseconds. So 20,000 divided by 1,000,000. So this would be 0.02 seconds, right? Which isn't even close. All right, so choice A is the correct answer there. So not only did you need to know how to convert giga, you had to be able to calculate the period from the given information and then be able to convert, all these metric prefixes. So a lot of sort of physics that goes into a question like that. Let's continue on with question 2 here from this question paper, which is a key foundational idea in physics that regarding base units. So they give us a question. Let me slide this over a bit. It says, at temperatures close to absolute 0 or 0 degrees Kelvin, the specific heat capacity C of a particular solid is given by C equals BT cubed, where T is the temperature and B is a constant characteristic of the solid. The SI unit for a specific heat capacity is joules per kilogram per degree Kelvin. What is the unit of constant B expressed in SI base units? So if we start with the equation, specific heat capacity is ET cubed. They tell us the unit, not in base units, right, but the SI units of specific heat capacity. So this side of the equation is joules per kilogram per degree Kelvin. It's really telling us how much energy do we need to put in 1 kilogram of a material to raise its temperature 1 degree Kelvin. Things like sand have a low specific heat capacity. Things like water have a pretty high specific heat capacity. So the same amount of energy incident upon both the sand and the water at the beach is going to affect those, materials differently. So the sand gets really hot very quickly because it doesn't, take too much energy to raise 1 kilogram of it 1 degree Kelvin. But for the same amount of energy, you're not raising the water's temperature as much, right? So the water is nice and cool on your feet, or the sand is burning your feet. That really has to do with specific heat capacity. All right, we know that the units of temperature over this side are Kelvin, and since it's cubed, it's going to be Kelvin to the 3rd power. And so now we have to figure out, well, what's going to be the units of B right here? Well, in order to get Kelvin in the denominator, we're going to have to cancel out 3 of those and have 1 more, right? So we know that whatever B is, it's got to have Kelvin to the 4th power in its denominator. And we can kind of see like all, these 2 answer choices have that. We're going to have to get a kilogram down there, right, to take care of that. And then I think we're all good here, besides we need joules up here. So joule per kilogram per Kelvin to the 4th are units, but they're not base units, right? So now we need to sort of say, well, what's a joule again? Different ways to think about what a joule of energy is. We could use an equation like work equals force times displacement. Say a joule of work is a Newton meter. We could remind ourselves that because F equals ma, a Newton of force is a kilogram meter per second squared, right? Those are the base units of a Newton. And so plugging that in for Newtons, we find that the base units of a joule are kilogram meters squared per second squared, right? So that's what a joule really is. You could use any equation for energy. You'd find you get the same thing. For example, if you did kinetic energy, mass is kilograms, and then meters per second. Once you square it, you get these meters squared per second squared. So it's kind of easy to see that that equation for energy gets the same base units, for joules of energy. There's another equation for energy, E equals mc squared, Einstein's famous, you see the same sort of physics there, right? Kilograms of mass, meters squared per second squared of velocity squared. So if we plug in this for joules here, we'd have, let's see, kilogram meters squared per second squared. See how I like the positive exponents? So that's just a joule. I still have this kilogram down here. We can see something's going to cancel. Still have this Kelvin to the 4th down here. And so the units of B are meters squared per second squared per Kelvin to the 4th, which looks like choice B, meters squared per second squared per Kelvin to the 4th. All right, so you have to know your equations. You have to know the SI units that sort of belong with the quantities, and then you've got to be able to boil it all the way down to the 7 base units, right? So there's a complete list of base units. There's only 7 of them, and some of them you don't even need for this course. 2 down, 38 to go.